Hey everyone, my name's Natasha, and today I'm going to be demonstrating a brief introduction to the programming language R. Now, there's a few features that make R unique. It's script-based and it's open source, so the language is constantly growing and improving as users develop new functions. Those functions are then often compiled as packages and stored in libraries that can be easily installed whenever you need them. There's actually an online database called CRAN, which stands for the Comprehensive R Archive Network, and it has over 18,000 free packages cataloged for public access. That versatility is what makes R uniquely powerful as a tool for statistical computing. You'll find that pretty much every scientific field uses it for data analysis these days, because honestly, you can do practically anything with it. Alright, let's get started. If you don't already have R and RStudio installed, you can do so from the links down in the description below. Make sure you download the actual R software before you download the RStudio IDE. The websites themselves should give you a step-by-step on how to install them correctly, but if you just follow the standard installation protocol for whatever your operating system is, you should be good to go. When you open up RStudio, you'll have a display that looks something like this, although I do think that the default color is white. But it's super easy to change the theme if you'd prefer dark mode or a different color scheme or a different sized font or anything like that. All you do is click on Tools in the top menu bar and then select Global Options at the bottom. Then navigate over to Appearance on the left and select your preferences. My personal favorite, as you can see, is Solarized Dark. If you're familiar with programming in other languages, you might recognize this left-hand panel as the console. The console can be used for running simple functions like arithmetic, and it also serves to interpret and output any code that you'd be running in an open source file. See, when I type in something like 2 plus 2 and press enter, it prints the answer. Or if you want, you could do even more complicated math expressions. You could do something like 4 cubed plus 11 times 81 and all of it divided by 6, and there you go, that's your answer. You could do the absolute value of a number by typing ABS and the number in parentheses, like so. Or you could calculate square roots with SQRT, again, followed by the number in parentheses. Then, if it starts getting cluttered, you can simply clear the console by pressing Ctrl-L. Super simple. There's dozens of other simple functions that are built into base R, and you can usually find them with a simple Google search, but for the sake of time, I'm not going to be covering them in this video. Feel free to take some time to play around with the console and just get comfortable with using it. It's capable of doing a lot, but it does get kind of messy to debug your code or perform a more complicated series of operations, or even go back and reference something later. If you want to write a program for a specific project, what you're going to want to do is make a fresh working directory with a blank script. To open up a new directory, click on File in the top left corner and select New Project. Then select New Directory, New Project again, and write a descriptive name for it. I'm going to call mine R Intro Tutorial. Make sure you save it to a file path you'll remember. Then click on File again and open up a new R script. This is where you'll actually be writing your code. Go ahead and save that new script by pressing Ctrl-S and give that a descriptive name as well. It's good practice to save your code incrementally as you work. Okay, let's start with creating some objects. An object in R is what we would call a variable in any other language. We could use the source file to do arithmetic just like we did in the console, but the output of that code just wouldn't be very useful. If we wanted to use the result of that arithmetic in more interesting ways, what we would have to do is first define an object and then assign that value to the object we just defined. Also, side note, but in R, pressing enter will start a new line, but if you want to interpret and output a line, you would press Control-Enter. So 2 plus 2, Control-Enter, and the answer 4 pops up in the console. Let's define a new object A. The assignment operator is an angle bracket and a dash to make an arrow, so we can use that to assign A the value 2 plus 2. Call A by typing the name of the object, hit Ctrl-Enter again, and there you go. The console returns the value 4 that we just saved to it. So now that object A has been defined, we're able to use it in other operations. For example, we could make a new object, say we could call it B, and assign it the value A times 10. Call object B the same way we did with object A, and as expected, it outputs the answer 40. This panel on the upper right is called the global environment, and what it does is it keeps a record of all of the different objects and data structures contained in your script. See right here, object A has an assigned value of 4 and object B has a value of 40. You can change the value of an object by just assigning it a new one. You could write a new statement like B and give it the value of 27.3 times 67, and the value of it will actually update in the environment. So this is also cool because it demonstrates that changing the value of an object in R won't change the value of any other objects. Whatever you enter as the most recent command will override all previous ones and become the newest stored value. Also keep in mind that you really don't have to call each object right after you define it. I'm only doing so for demonstration purposes so that you guys can see the output directly in the console. Alright, so in addition to numerics, the two other most common data types you'll probably see are characters and logicals. Characters are just text values. It's as simple as that. You can assign an object any string of letters or words as its argument so long as you enclose them in quotation marks. For example, we can make the new object character and assign it the value hello world. Logicals are just a little bit more complicated. The best way I could describe them is as a true or false statement that results from a relational expression. A really simple example would be an inequality, like 2 is greater than 7. As far as I'm concerned, 2 is not in fact greater than 7, so the logical statement that results from it is false. And you can see down here, when you ask R whether or not 2 is greater than 7, it outputs false. On the flip side, 8 is greater than 5 would generate the output true, and you can verify that both in the console and the global environment. Alright, so we've got greater than, we've got less than. The other relational operators you're going to see are equal to, which is notated as a double equal sign, not a single one, and not equal to, which is represented by an exclamation point followed by an equal sign. There's also something called a logical operator, which is a symbol that can bind multiple relational statements together. By that, I mean something like this. We could make a new value logical 4, super original, I know, and assign it 6 is less than 8, or 9 is greater than 11. That line down the middle means or. So basically, logical 4 will evaluate as true if 6 is less than 8, or if 9 is greater than 11. Since at least one of the expressions satisfies the statement, our logical output is considered to be true. The other logical operator is an ampersand symbol, meaning and it works exactly how you'd expect it to. We could make my logical 5 and assign it the value 4 is not equal to 7 and 6 is greater than 1. And it'll evaluate to true because both of those statements are correct. Before we move on, one really important piece of syntax to know is how to comment out your code. In R, this is done by either starting a line with a hash mark or by selecting a line and pressing Ctrl-Shift-C. Let's add a comment right here. We can say logical operators bind multiple relational statements together. Any line in R that begins with a hash mark won't be interpreted as code, so this is super handy for writing descriptions or captions or any other notes you might need. You can also put a comment in the same line as an existing line of code, like so. Alright, now let's talk about vectors. Vectors are one of the most common data structures in R, and basically all it is a self-contained series of values. Since a vector is just another type of object, making one follows the same steps. You just give it a name, use the assignment operator, and then you add the letter C, followed by whatever values you want in parentheses. That letter C stands for concatenate, which basically means to link things together in a series. So you could make a vector of numeric values, like we just did, or you could make a vector of characters like this. You could give it the values blue, red, and green. Or if you really wanted, you could even make a vector of logicals, which would look something like this. Kinda gnarly looking, yeah, but you'll see that it correctly evaluates each item in the vector against whatever condition you supplied. In this case, it goes down the line and checks whether or not each of those values is greater than 10. So as you can see, it outputs false, true, true, false, because 9 is not greater than 10, 23 and 35 are greater than 10, and 4 is not either. No matter what the data class is, all of the values in a vector have to be separated with commas so that R knows to read them as individual items. And when you're working with characters, each value must be enclosed within double quotes. If not, R will try to read them as objects, and since those objects don't actually exist, it'll return an error message. Here, let me just demonstrate that real quick. Delete the quotes surrounding blue, and yep, error, object blue, not found. Okay, let's just return those quotes. Another thing about vectors is that all of the values inside have to be the same data type. So here, we could make a fourth vector with a character value followed by a numeric value, and just toss in a logical statement for good measure. When I hit Control-Enter, you'll notice in the environment that R literally forces the values into one common data type. Since it can't really convert the word blue into numbers, it instead reads the other values as strings, putting them in quotes. There's tons of pre-existing functions that you could use to interpret vectors. There's the length function, which tells you how many elements you have, or the class function to ID the class of a vector, kind of self-explanatory, and so on and so forth. These commands might all seem a little bit silly when you're working with a 3-item vector, but they are super handy whenever you have to analyze larger and more complicated datasets. Speaking of which, I think it's time to introduce MT-cars. R has a few built-in datasets that people use for testing whether or not their code works, and weirdly enough, one of the most popular ones is this collection of car data from some random magazine in the 70s, and it's called MT-cars. Since MT-cars already exists in R without us doing anything, we can open up its contents by just calling its name. Usually the process for opening a dataset is a little more involved, but we can talk about that some other time. Okay, so let's check out MT-cars. You can see here that we've got a list of different car models followed by a bunch of stats about the make and performance of each one. If we use the class function that I mentioned earlier, class parentheses MT-cars, it tells us that MT-cars is a data frame. A data frame is kind of like a cross between a matrix and a list. Essentially, it's a bunch of same-length vectors all stacked next to each other. In this situation, the structure function would be very useful. Just type str parentheses MT-cars. And what that does is it quickly generates a breakdown of the structural features of the dataset. See, it tells you the class, the number of variables, and the number of observations for each variable. If you only need to see a snippet of that data frame, you could use the head function. And that'll output only the first 6 rows of the data frame. For anyone looking to use R as a stats tool, you are going to massively appreciate this next function. Summary, parentheses MT-cars. It's not super detailed, but look, R was just able to crank out a rapid stat summary for every single variable in our dataset. It tells you the minimum, the maximum, the average, and even the quartile values if you needed to calculate the IQR. Say we just want to look at a single variable, just one column in MT-cars. We could do that using the $sign operator. Okay, tight. So now we isolated the miles per gallon data, and that technique we just used is called subsetting. We could check what the data class is for a single variable in our dataset by combining the $sign operator with the class function we mentioned, like this. So now we know that miles per gallon is a numeric data type. If you want to extract a specific value from that column, we could do something called indexing. You just retain that syntax and then in brackets put the position of the value we're looking for. For example, if we wanted to extract the value in position 7, we would index it and get 14.3. You can also index using both row and column positions, sort of like coordinates. So if we want to know what value is in row 13 and column 4, we can index it, and there, you get 180. If we write a similar command but leave the column position empty, R will subset all of the columns for the selected row, and vice versa. So subset all columns for row 9 and it outputs the values for every variable of that specific make and model. Or subset all rows for column 6 and it outputs the weight values for every model in that dataset because the variable in column 6 corresponds with weight. If you wanted to really narrow down your subset, you could set a range for both positions, like rows 2 to 7 and columns 1 through 5, and it'll subset for the parameters you entered. You just use the colon to indicate the range. Or say you want to know the gas mileage of a particular model of car. You can index by both row name and column name like this. Again, since the name of the variable is a character, make sure you enclose both of them in quotes. You could also index multiple positions simultaneously if you nest a vector within the brackets. By that, I mean you could isolate a row for a particular vehicle and then select which variables you want shown by concatenating their positions. So empty cars, we can go for the Mazda RX-4, and we want columns 1, 3, 4, and 9. And there you go. Just to refresh you guys on some of the concepts we covered earlier, you could also subset your data using relational statements. So we could filter out all of the vehicles that get under 20 miles per gallon and make a subset of the cars with gas mileage above that. Since we want all of the columns to be included in this subset, we could leave the column position in the brackets empty. You could also save the conditions of a subset to an entirely new object. So, for example, you can make a whole new object called parameters, and then only assign it values that get, say, over 20 miles per gallon, has 4 cylinders, and has anything but 1 carburetor. Then you could use the object parameters as the row index to subset empty cars, and then force it to print out whatever the results are. So this subset we just made is now exclusively comprised of cars that get over 20 miles per gallon, has 4 cylinders, and has any number other than 1 carburetor. Up till now, we've been outputting our results in the console by simply calling the name of the object. But like I just demonstrated, you can force R to interpret and print out any command by using the print function. Alternatively, there's also a more straightforward way to save a subset to its own object. We could just make one, like myCars, and assign it the value of empty cars with bracketed conditions. So for the rows, we could make a subset that includes vehicles with a horsepower over 107, something arbitrary like that. And for the columns, we could subset everything except for column number 6, and we can do that using the minus sign operator. The minus sign operator can be used to omit numeric values from a dataset. Unfortunately, this means that it cannot be used to exclude any characters. So if we tried to make a parameter that, say, excludes all cars matching the name Pontiac Firebird, it gives us an error message that says invalid argument to unary operator. But now that myCars exists as its own object, you're free to subset and index that however you want. We could check the class of it and see that it's still a data frame, that hasn't changed. And when we check the structure of it, we can see that it only has 22 observations of 10 variables, whereas empty cars has 32 observations of 11 variables. There's one last way we could subset data using only the functions in base R, and that is with the subset command. We'll start by making a new object to assign value to. And to use the subset command, you basically need 3 components. The first is the name of the dataset, the second is the rows that correspond to whatever condition you supply, and the third is the columns that you want retained. So when we call object myCars1, you will see that the data has been perfectly consolidated as we requested. It works exactly how the other subsetting methods do, but this one is just its own little built-in function. Okay, I feel like I've been talking for a super long time, so I'm gonna wrap up this lesson here. Hopefully this was a helpful introduction to programming in R. If you're a veteran coder, I do apologize if it was a little on the basic side. In part 2, I'm going to be picking up where we left off with data manipulation and teach you all about packages and plotting using ggplot2. Feel free to leave a like and subscribe if you want. No pressure though, and I'll see you all next time.